At the very heart of our Milky Way galaxy lies an extraordinary object, a supermassive black hole. This invisible monster, known by its formal designation as Sagittarius A, pronounced Sagittarius A star, plays an undeniably central role in shaping the structure and behavior of our galactic home. But how does a single, unseen entity so far away manage to influence a star system that stretches over 100,000 light-years from end to end? To answer that, we need to understand a bit more about what Sagittarius A is, how it formed, and what its presence means for the Milky Way. A black hole forms when a massive amount of matter is squeezed into a very small space, creating a region of space where gravity is so strong that nothing, not even light, can escape. Supermassive black holes like Sagittarius A are incredibly dense, containing millions, sometimes billions, of times the mass of our Sun, but compressed into an area just a few times the size of the solar system. Scientists are confident that such black holes reside at the centers of many galaxies, and they are thought to be essential to galaxy formation and evolution. Sagittarius A has the mass of about 4 million suns, packed into a region no larger than our solar system. Although it cannot be seen directly, because it traps all light and radiation, astronomers detect its presence by studying the orbits of nearby stars and gas clouds. These objects move at incredible speeds, whipping around the black hole due to its intense gravitational pull. Tracking these orbits gives scientists a way to measure the mass and location of Sagittarius A. This method of investigation reached new heights when, in 2020, the Nobel Prize in Physics was awarded to researchers who precisely monitored stars near the galactic center, providing solid evidence for the existence of a supermassive black hole there. The influence of Sagittarius A extends far beyond just pulling on nearby stars. Its gravity acts like the anchor point for the entire Milky Way, helping to maintain the galaxy's coherent shape. Picture the Milky Way as a vast, rotating disk of stars, gas, dust, and dark matter. Without something in the middle holding it all together, these materials might simply drift apart. The black hole's gravitational pull isn't the sole force at work. Dark matter, a mysterious and invisible substance that makes up most of the universe's mass, also contributes. But Sagittarius A is a key player in the complex gravitational balance. What's especially fascinating about Sagittarius A is that, unlike the often destructive image of black holes swallowing up everything in sight, our galaxy's central black hole is relatively quiet now. It's not actively feeding on large amounts of matter, so it doesn't emit the intense energy and radiation that some black holes do when they consume stars or clouds of gas. However, in the distant past, and possibly even in the future, it may have undergone periods of intense activity. During these active phases, the black hole's accretion of material would have produced enormous amounts of energy, influencing star formation and the overall behavior of the galaxy. Astronomers observe other galaxies featuring active supermassive black holes known as quasars, which shine with more light than entire galaxies because of the energy released as matter falls in. Our own black hole is currently quiet in comparison, but understanding its history helps us learn how galaxies evolve over billions of years and how central black holes influence their environments. One of the remarkable breakthroughs in studying Sagittarius A came recently with the development of the Event Horizon Telescope, EHT, a global array of radio telescopes designed to effectively act as a giant Earth-sized observatory. In 2019, the EHT collaboration released the first-ever image of a black hole's shadow, specifically of one at the center of the galaxy Milky Way, showing the dark silhouette of the black hole surrounded by glowing gas. This success has propelled further efforts to image Sagittarius A despite challenges, like the rapid movement of gas clouds around our galactic center. Studying Sagittarius A also advances our understanding of fundamental physics. Black holes serve as natural laboratories for testing Einstein's theory of general relativity, which describes how gravity works on cosmic scales. In extreme environments like near the event horizon, the boundary around a black hole beyond which nothing can return. Gravity becomes incredibly strong and behaves in ways that are different from everyday experiences. Observations of stars very close to Sagittarius A can reveal tiny deviations in their orbits, allowing scientists to test predictions of general relativity against actual data and look for hints of new physics. Moreover, black holes challenge our understanding of quantum mechanics and gravity, two pillars of physics that don't yet fully reconcile at the extremes found near these objects. By probing the environment around Sagittarius A, scientists hope to make progress toward a more unified theory of physics that could explain both the very large gravity and spacetime, and the very small particles and quantum fields. While Sagittarius A remains invisible to our eyes, its presence shapes the Milky Way in many visible ways. For example, its gravitational influence helps regulate the distribution of stars and gas, which in turn affects star formation rates. The flow of gas towards or away from the center can trigger bursts of new stars or regulate the growth of the galaxy's central bulge. Additionally, the black hole's environment is home to unique phenomena such as powerful magnetic fields and intense radiation, which play roles in processes like cosmic ray acceleration and shaping the interstellar medium. Our understanding of Sagittarius A continues to grow thanks to advances in technology, including space telescopes like the Chandra X-ray Observatory and instruments operating across the electromagnetic spectrum. These telescopes reveal the high-energy environment near the galactic center, tracking flares of X-rays and infrared radiation that occur when small amounts of material briefly fall into the black hole, creating bright outbursts detected from Earth. The study of Sagittarius A is far from a static field. Future projects such as the James Webb Space Telescope and improvements in gravitational wave detectors will provide even more detailed data. These developments may reveal how frequently our black hole experiences feeding events, how it interacts with surrounding stars, and possibly how it has influenced the Milky Way's evolution over billions of years. Understanding Sagittarius A also connects to a larger cosmic story. Every large galaxy observed seems to harbor a supermassive black hole at its core, suggesting a fundamental link between the growth of these objects and their host galaxies. By studying ours up close, we gain insight into galactic formation and behavior across the universe, from the smallest dwarf galaxies to the largest collections of stars. In summary, Sagittarius A is much more than a distant, invisible mass. It is a central architect of the Milky Way's structure and dynamics, an active participant in cosmic processes, and a doorway to understanding some of the most profound physical laws of nature. As observational techniques improve and theoretical research advances, the mysteries wrapped around this black hole promise to be a focal point for astronomical discovery and curiosity for years to come. To truly appreciate the role of Sagittarius A in our galaxy, it helps to understand the dynamic environment around this supermassive black hole, specifically, how matter behaves in its vicinity, and how this influences the broader galactic ecosystem. One of the key concepts here is the accretion disk, a structure formed by gas, dust, and other materials spiraling inward toward the black hole. While Sagittarius A is currently relatively quiet, the presence and behavior of these disks are crucial to grasping how black holes interact with their surroundings. An accretion disk forms when matter gets caught in the intense gravitational pull of a black hole, but still possesses some angular momentum, meaning it spins somewhat as it falls inward. Instead of plunging directly into the black hole, this matter orbits and gradually loses energy, causing it to spiral closer to the event horizon, the boundary beyond which nothing can escape. As the gas and dust in the accretion disk swirl around at enormous speeds, friction and magnetic forces cause the material to heat up dramatically, reaching temperatures of millions of degrees. This process emits radiation, often in the form of X-rays and other high-energy light, which is how astronomers detect active black holes even when the black hole itself emits no light. Despite extensive observation, Sagittarius A does not exhibit a bright, stable accretion disk like those seen around supermassive black holes in more active galaxies. Instead, the region around it is characterized by a relatively low level of matter inflow and intermittent flares, where small amounts of gas fall in. This leads to bursts of X-rays and infrared radiation that are detectable but much weaker than the brilliant emissions from active galactic nuclei, or AGNs, found in more energetic galaxies. The current quiet state of Sagittarius A gives us a unique chance to study a supermassive black hole that has settled into a comparatively peaceful phase, offering insight into how these phenomena might cycle between activity and dormancy over cosmic timescales. Besides the accretion disk's simple presence or absence, the environment near Sagittarius A reveals complex magnetic fields and turbulent motions of hot plasma. Magnetic fields play a fundamental role in regulating the behavior of matter close to the black hole, helping to channel energy, accelerate particles, and sometimes even launch jets of material at nearly the speed of light. Although Sagittarius A doesn't currently produce large-scale jets like some other black holes do, scientists continue to investigate whether smaller, less obvious ejections of material occur, and what impact these may have on the surrounding interstellar medium. The plasma near the black hole also generates what's known as synchrotron radiation, a process where charged particles, like electrons, spiral along magnetic field lines at relativistic speeds. This radiation stretches across a range of wavelengths, from radio waves to X-rays, and is an important diagnostic tool users employ to understand the physical conditions near the event horizon. By studying fluctuations in this radiation, astronomers learn about the density, temperature, and magnetic properties of the environment, unveiling a highly energetic and dynamic zone despite the overall calm reputation of Sagittarius A. The interplay between the black hole and the surrounding material doesn't stop at electromagnetic phenomena. The gravitational influence of the central black hole shapes the orbits of stars clustered tightly around it, known as the nuclear star cluster. This dense gathering of stars has been a major focus in understanding Sagittarius A, especially since some of these stars orbit extremely close to the black hole, some even within just a few light days, which on a cosmic scale is remarkably close. One star, in particular, named Estwo, has been tracked closely by telescopes over many years. It completes one full orbit around Sagittarius A every 16 years, moving at speeds up to a few percent of the speed of light at its closest approach. Studies of Estwo's orbit have provided some of the strongest evidence supporting the existence of a supermassive black hole, because its movement matches precisely the predictions made by Einstein's general theory of relativity. When Estwo swings near the black hole, its orbit shows subtle effects such as gravitational redshift, where light loses energy climbing out of the black hole's gravitational well, and the precession of its orbit, a relativistic effect where the orbit shifts position slightly over time. These observations are not just confirmations of theory, they also serve as laboratories for testing physics under extreme gravity. Researchers hope that continued monitoring might even reveal discrepancies hinting at new physics beyond Einstein's model. By observing multiple stars in the nuclear cluster, scientists gain a more complete picture of how gravity behaves at these intense scales, and how the distribution of matter around the black hole affects stellar motions. Another fascinating aspect of the galactic center is that it is home to various exotic objects beyond ordinary stars and gas. For example, researchers have found unusual and extremely dense stars such as magnetars, neutron stars with immense magnetic fields, and stellar remnants that have survived passage through the tumultuous center. Studying these tells us about the life cycle of stars influenced by the black hole's gravity. The dense environment around Sagittarius A also facilitates interactions such as close encounters between stars, binary system disruptions, and even collisions, which can influence everything from star formation rates to the feeding patterns of the black hole itself. While Sagittarius A's current activity is modest compared to the intense outbursts seen in quasars. Evidence from other wavelengths suggests that it may have been much more energetic in the past. Traces of these past eruptions appear as large structures thousands of light-years across, such as the Fermi bubbles, huge lobes of gamma-ray emission extending above and below the galactic plane. These colossal features are believed to be remnants of energetic events involving Sagittarius A, possibly triggered by bursts of rapid accretion hundreds of thousands to millions of years ago. Such events could have had significant effects on the distribution and temperature of gas in the galaxy, potentially influencing star formation and the galaxy's evolution. Understanding the timing, triggers, and consequences of such activity cycles is a central challenge in astrophysics. By piecing together data from different observations and simulations, scientists hope to uncover why and how black holes transition between active feeding phases and quieter periods. Variables such as the supply of gas, interactions with nearby stars, and broader galactic dynamics all play roles in this complex picture. On a larger scale, the presence of Sagittarius A connects to fundamental questions about galaxy formation. The observed correlation between the mass of supermassive black holes and the properties of their host galaxies, such as the bulge mass and velocity of stars, suggests a coevolutionary relationship. It appears that the growth of black holes and their galaxies is intertwined. As matter falls into the black hole, energy and momentum released can regulate the inflow of gas, affecting star formation and galaxy growth in a feedback loop. This process is known as AGN feedback, when active galactic nuclei produce outflows or radiation that impact the host galaxy. In the case of the Milky Way, the relative calm of Sagittarius A provides a local example where the interplay is subtle but ongoing. It also offers a vital reference for comparing more extreme and active galaxies. By understanding the activity cycle and environmental impact at the center of our own galaxy, astronomers refine models that help explain a vast diversity of galactic behaviors observed across the universe. Looking forward, researchers plan to combine data not only from telescopes that observe light across many wavelengths, radio, infrared, X-ray, gamma-ray, but also from instruments detecting other cosmic messengers. For instance, gravitational wave observatories might, in the future, detect ripples produced by stellar remnants interacting with Sagittarius A or mergers, involving smaller black holes near the galactic center. These detections would offer entirely new ways to probe the region beyond electromagnetic signals. Meanwhile, technological improvements and novel observing techniques are continuously pushing boundaries. The use of adaptive optics on ground-based telescopes sharpens images distorted by Earth's atmosphere, enabling even more precise measurements of star motions. Upcoming facilities like the Extremely Large Telescope, ELT, will provide unprecedented resolution to observe the galactic center in fine detail, potentially detecting smaller stars or gas streams previously hidden. In summary, the environment surrounding Sagittarius A is a complex, dynamic zone where gravity, magnetism, radiation, and matter interact to shape the heart of our galaxy. Although this supermassive black hole is not currently the cosmic powerhouse seen in more active galaxies, its subtle influences govern the behavior of stars and gas nearby, and hold clues to understanding galaxy evolution at large. By studying Sagittarius A, we gain insight into fundamental physics, stellar dynamics, and the ongoing story of the Milky Way's formation and development. Beyond the immediate region surrounding Sagittarius A, the presence of this supermassive black hole influences the Milky Way on much larger scales, shaping the structure and dynamics of our entire galaxy. One important example of this influence is the way Sagittarius A helps to anchor the motion of stars, gas clouds, and dark matter, ensuring that the galaxy maintains its iconic spiral shape. Galaxies like the Milky Way are composed of multiple components: a central bulge of densely packed stars, a flat disk containing most of the stars and gas arranged in spiral arms, a surrounding halo filled with dark matter and few stars, and a vast population of stars scattered across the galactic plane. The gravitational pull from the black hole at the center complements the forces from the mass distributed throughout these components, helping to stabilize orbital paths and regulate the velocities of objects as they rotate around the galactic core. The way stars orbit the galaxy is a testament to this gravitational balance. If the central mass were missing or significantly smaller, stars farther from the center would exhibit very different rotations, potentially flying off into intergalactic space or collapsing inward. Instead, stars in the Milky Way move in a manner consistent with what astronomers call differential rotation, where stars closer to the center orbit faster than those farther out. This pattern is influenced not only by the black hole, but also by the combined mass of stars, gas, and a mysterious substance called dark matter, which makes up roughly 85% of all matter in the universe, yet has never been directly observed. How exactly does dark matter fit into this picture? While Sagittarius A exerts an intensely localized gravitational pull, dark matter appears to form an extended, invisible halo around the galaxy, contributing the bulk of the galaxy's mass. Without this dark matter halo, the orbital speeds of stars in the outer parts of the Milky Way would slow down with distance from the center, as classical gravity predicts. Instead, observations reveal that stars move much faster than expected at those distances, implying there's extra mass that doesn't emit or interact with light directly. Together, the black hole, luminous matter, and dark matter form a complex gravitational landscape that keeps the Milky Way stable and rotating. On a smaller scale but still crucial to the life of the galaxy is the role Sagittarius A plays in influencing star formation in the central regions. The gravitational forces around the black hole can trigger compressions in nearby gas clouds, causing them to collapse and ignite star formation. Conversely, the energy released during active phases of the black hole can clear out gas reservoirs, temporarily suppressing the birth of new stars. This push and pull between feeding the black hole and giving birth to new stars is a delicate balance informed by observations across many galaxies, including our own. Additionally, Sagittarius A is intricately linked with the galactic bulge, a densely packed spherical concentration of stars enveloping the central black hole. The properties of this bulge correlate closely with the mass of the black hole itself. Astronomers have found a surprising relationship known as the M-sigma relation. The mass of a supermassive black hole in the center of a galaxy is roughly proportional to the velocity dispersion, random motions, of stars in the surrounding bulge. This connection suggests that the growth of supermassive black holes and their host galaxies is a coevolutionary process, where each influences the other over billions of years. To understand this coevolution, scientists use simulations and models that integrate gravity, fluid dynamics, star formation, and feedback processes. These simulations show that when a black hole actively accretes material, it can radiate intense energy outward, driving powerful winds or jets that push gas away from the galactic core. This feedback regulates both the black hole's growth and the rate of star formation, preventing the galaxy from becoming excessively dense or producing too many stars too quickly. Over cosmic time frames, such feedback shapes the galaxy's size, composition, and appearance. In the Milky Way, Sagittarius A's current quiet state suggests it is in a phase where such feedback is limited. However, past episodes of activity likely played a role in defining the structure we see today. The enormous Fermi bubbles, enormous lobes of high-energy gamma-ray radiation stretching above and below the galactic plane, are prime candidates for remnants of such energetic outbursts. These bubbles span roughly 25,000 light-years each, and indicate that the galaxy underwent significant energetic events perhaps a few million years ago, possibly due to a sudden influx of matter into Sagittarius A. The existence of these Fermi bubbles also raises broader questions about how energy and matter transported by a black hole's activity influence the larger galactic environment. The bubbles interact with surrounding gas through shocks and heating, altering the efficiency with which new stars can form in these regions. This demonstrates that the influence of Sagittarius A extends well beyond the immediate surroundings of the black hole, affecting the Milky Way's evolution on a truly vast scale. Further evidence for black hole-driven outflows comes from observations of high-velocity gas streams and molecular clouds near the galactic center, moving at hundreds of kilometers per second. These gas motions appear consistent with being blown or accelerated by past outbursts from Sagittarius A. By studying such features, astronomers aim to understand the timing, magnitude, and triggers behind these events, piecing together a timeline of the black hole's feeding history. Another key area of study focuses on the interaction between Sagittarius A and the dense cluster of stars packed within a few light-years of the galactic center. This nuclear star cluster stands out as one of the densest clusters in the Milky Way, containing a mixture of older population stars, young massive stars, and exotic remnants like neutron stars and black holes. The environment is highly dynamic, with stars frequently undergoing close encounters that can alter their paths, form new binary systems, or even be flung out of the cluster altogether. One particularly fascinating outcome of these dense interactions is tidal disruption events, where a star ventures too close to the black hole and is torn apart by its immense gravitational forces. When this happens, roughly half of the star's material is stretched into an elongated stream, some of which eventually spirals into Sagittarius A, causing a bright flare as the gas heats up and emits radiation. Although no definitive tidal disruption event has been observed in the Milky Way's center in recent decades, astronomers expect such events to occur on average about once every 10,000 to 100,000 years. When they do, they provide rare glimpses of black hole feeding processes and can temporarily light up the otherwise quiet environment. Even more subtle gravitational effects are observed through phenomena such as gravitational lensing, where the immense gravity of Sagittarius A and stars around it bends and distorts the path of light from background objects. This effect enables astronomers to detect otherwise hidden masses and test predictions of how gravity operates near a supermassive black hole. By tracking how light bends and changes, researchers can infer properties of the spacetime around Sagittarius A, offering indirect yet powerful evidence supporting general relativity and advancing our understanding of gravity in the strong field regime. In addition to electromagnetic observations, a new frontier is opening in the form of gravitational waves, ripples in spacetime produced by massive accelerating bodies. Although the most famous detections so far involve merging black holes or neutron stars in distant galaxies, the environment around Sagittarius A may also generate gravitational waves through interactions with smaller black holes, stars, or dense stellar remnants. Future detectors with enhanced sensitivity could pick up these subtle signals, providing new ways to study the black hole's neighborhood and revealing hidden populations of objects orbiting close to the event horizon. The combination of all these observations, from stars' orbits and flares to gas flows, radiation, and gravitational waves, creates a comprehensive picture. Sagittarius A is not merely a passive, invisible trap in the center of the Milky Way. It is an active participant in a complex system. The black hole affects the fate of gas clouds, regulates star birth, sculpts the distribution of stars, and leaves imprinting marks on the galactic environment extending thousands of light-years outward. Our growing technological capabilities promise even more discoveries. For example, the next-generation Event Horizon Telescope observations aim to capture detailed images of Sagittarius A's immediate surroundings, showing the event horizon's silhouette against hot, glowing gas. These images will help test theories of how matter behaves under extreme gravity, including exotic predictions about how event horizons actually appear. Similarly, upcoming instruments like the Extremely Large Telescope, ELT, will enable astronomers to monitor faint stars even closer to the black hole than those tracked so far. Detecting these tiny orbits will push tests of gravity further, and could reveal new populations of objects formed or influenced by Sagittarius A's immense pull. On larger scales, planned space missions will study the Milky Way's overall structure with higher precision, revealing how the galaxy's shape and rotational dynamics continue to be affected by the central black hole and its history of activity. Through all this, Sagittarius A remains central to one of the most exciting scientific quests, understanding how black holes and galaxies grow and evolve together. Our own galaxy, with its quiet yet powerful heart, serves as an accessible laboratory, close enough for detailed observation, yet complex enough to challenge and refine our understanding of the universe. In essence, Sagittarius A is both a product and a driver of cosmic evolution, a gravitational anchor, an engine of change, and a window into physics under the most extreme conditions. The study of this supermassive black hole continues to deepen not only our knowledge about the Milky Way, but also fundamental questions about the origins and ultimate fate of galaxies throughout the cosmos. Building on this intricate picture, it's important to consider how Sagittarius A fits into the broader framework of cosmic evolution, not just within the Milky Way, but across the universe. Observations have shown that many galaxies, regardless of their size or shape, harbor supermassive black holes at their centers. This common feature suggests that these black holes and their host galaxies are tightly linked through their life cycles. Understanding how this relationship develops over billions of years requires exploring both theoretical models and comparisons among diverse galactic environments. One key idea in modern astrophysics is that supermassive black holes like Sagittarius A grow alongside their galaxies through a process called coevolution. Essentially, as a galaxy accumulates gas, dust, and stars, some of that material eventually makes its way toward the central black hole, allowing it to gain mass. Meanwhile, energy released during periods of intense accretion can affect the surrounding galaxy by heating and expelling gas, influencing the rates at which new stars form. This feedback loop means the black hole is not merely a passive bystander, but an active agent shaping the galaxy's growth and structure. To explore this coevolution, scientists study correlations between black hole mass and various galactic properties. The M-sigma relation mentioned earlier reveals that galaxies with larger, more massive central bulges tend to have heavier black holes. This correlation is so tight that it implies a causal connection, though the specific mechanisms remain a topic of ongoing research. For example, does the black hole regulate star formation by blowing away gas, or does the galaxy's growth funnel more matter into the black hole? Most likely, both processes happen together, influenced by complex dynamics including galaxy mergers, gas inflows, and starburst activity. Galaxy mergers, in particular, play a significant role in black hole growth and galaxy evolution. When two galaxies collide and eventually merge, their central black holes may also approach one another, and over time, coalesce into a larger black hole. These events can trigger bursts of star formation and increase the density of gas near the galactic center, feeding the black hole and potentially igniting a quasar phase, the brightest and most energetic stage of active galactic nuclei. During quasar phases, the intense radiation and powerful jets can dramatically reshape the host galaxy, driving outflows that control the availability of star-forming material. While the Milky Way currently experiences a relatively calm epoch in this context, it will eventually merge with the nearby Andromeda galaxy in about 4 billion years. This impending collision is expected to alter the activity of Sagittarius A significantly. The gravitational turmoil and inflow of gas resulting from the merger may awaken the central black hole, potentially transforming our galactic center into an active galactic nucleus with increased brightness and energetic outputs. Such events are not just theoretical. Astronomers see plenty of galaxies in the universe caught in various stages of merger and black hole activity, providing real examples of these evolutionary pathways. Another area of active research involves the seeds from which supermassive black holes like Sagittarius A initially form. Although we know that black holes result from collapsing stars or the direct collapse of gas clouds, it remains unclear how those early seeds grew so quickly in the young universe to reach millions or billions of solar masses. Some hypotheses propose that dense clusters of massive stars or primordial gas clouds collapsed directly into black holes a few 100,000 years after the Big Bang, providing the starting mass for rapid growth through accretion and mergers. Studies of distant quasars, some shining brightly at times when the universe was less than 1 billion years old, challenge models of gradual black hole growth and require explanations accommodating rapid early mass accumulation. The study of Sagittarius A thus connects observational astronomy with cosmology, as insights gained from our own galaxy's center inform models of black hole and galaxy formation throughout cosmic history. These connections emphasize how local investigations of Sagittarius A serve as a laboratory for understanding universal processes. On a more detailed level, modern technology is refining our ability to map the structure and dynamics within the galactic center region. Advances in interferometry, techniques that combine signals from multiple telescopes, have enabled astronomers to achieve incredibly high resolutions, resolving features on scales comparable to the size of our solar system, but located over 26,000 light-years away. This precision lets researchers detect phenomena such as clumps of gas, magnetic field configurations, and potentially even smaller black holes orbiting Sagittarius A. These smaller black holes, remnants of massive stars from earlier generations, are expected to populate the center of the Milky Way in large numbers. Finding and studying them could reveal the processes that govern stellar evolution and death in extreme environments, and improve our understanding of binary systems and gravitational wave sources. For example, mergers between smaller black holes orbiting near Sagittarius A could produce gravitational waves detectable by next-generation observatories. Detecting such waves from the galactic center would offer a complementary way to study the black hole's environment beyond electromagnetic observation. Additionally, the galactic center acts as an exceptional region for investigating the interplay between gravity and magnetic fields. Magnetic fields near Sagittarius A influence the motion of charged particles in the accretion disk and surrounding plasma. Studies show that these fields can be highly ordered over surprisingly large scales, despite the chaotic nature of the environment. Understanding magnetic field structure aids in explaining mechanisms behind particle acceleration, jet launching, even if jets are currently weak or absent in Sagittarius A, and the heating of surrounding gas. Observations across multiple wavelengths continue to uncover new features and behaviors. For example, radio waves help pinpoint synchrotron radiation from electrons spiraling along magnetic field lines, while infrared light penetrates dust clouds better than visible light, revealing stars and gas previously obscured. X-ray and gamma-ray telescopes detect energetic flares and outbursts, indicative of the black hole's feeding episodes or shock waves propagating through the galactic center's medium. Looking ahead, instruments like the upcoming Lynx X-ray Observatory and the European Space Agency's Athena mission promise to provide orders of magnitude improvements in detecting faint X-ray emissions from Sagittarius A and its surroundings. These enhanced observations could uncover weaker signals associated with more subtle black hole activity or with the hot gas interacting with the nuclear star cluster. Another exciting frontier is the study of the direct gravitational environment around Sagittarius A via the orbits of stars that venture closest to the event horizon. Improvements in adaptive optics and infrared detectors allow astronomers to track these S-stars with ever greater precision. Detecting currently unknown relativistic effects such as frame dragging, a phenomenon where the rotating black hole twists the fabric of spacetime, could happen within the next decade. Such measurements not only put Einstein's theory to the test, but might also expose deviations that hint at new physics or reveal the nature of dark matter in the galactic center. Moreover, Sagittarius A plays a significant role in the formation and evolution of the Milky Way's bar and spiral arms, large-scale structural features of the galaxy. The bar, an elongated dense region of stars passing through the galactic center, helps channel gas inward by creating gravitational torques that funnel material towards Sagittarius A. This inflow influences star formation, rates near the center, and the growth of the nuclear star cluster. Understanding these processes is key to linking activity in the galactic core to broader galactic architecture. On that note, the spiral arms themselves contain sites of ongoing star formation, dense molecular clouds, and collections of young stars, all shaped partially by gravitational forces extending outward from the central regions. Sagittarius A's gravitational presence impacts these orbits indirectly, contributing to the overall rotation curve of the Milky Way, and therefore influencing how material organizes itself on a galaxy-wide scale. In understanding our place in the Milky Way, Sagittarius A stands out as a silent yet dominant force, informing not only the motions of stars and gas, but also the cosmic history that has led to the formation of our solar system, and ultimately, life on Earth. By studying this supermassive black hole and its environment, scientists piece together a narrative that stretches from the birth of the universe to the present day, and will continue to evolve long into the future. The research into Sagittarius A is a testament to human curiosity and ingenuity, blending observational astronomy, theoretical physics, and cutting-edge technology to uncover the workings of an object that remains invisible to our eyes, but essential to our understanding of cosmic structure. As new instruments come online and computational models grow more sophisticated, the story of the black hole controlling our galaxy will undoubtedly become clearer, revealing deeper insights into the fundamental nature of gravity, matter, and the universe itself.